momentum and it's non-relativistic. How do I know that it's non-relativistic? I know that that the mass of the nucleus is very large compared to the momentum. So the energy, the rest energy of the nucleus is whatever this thing is. What was? Well, I don't know what the A was.
They don't tell you.
Oh, they didn't say. Well, it's some large number of GeV, and this is MeV, so that it's a tiny fraction. So this is a non-relativistic.
That's what I forgot.
Just because the energy is too low?
Hmm?
The energy is
is
just-
way too low.
Because the electron is just so freaking small.
But for the electron, which has an energy, a rest mass of half an MeV, then it's very much relativistic. It's got a, you don't officially know what a relativistic gamma factor is, but it's the ratio of the energy to the rest mass.
So what did you guys get doing the classical?
9.1.
Yeah, like 9 EV or something.
I just figured it's chapter 1 of Goldstein. You can't expect this in relativity yet.
No, right. Just know that it.
That's good. I love that logic.
You've
Yeah, that's
presumably been
exactly
around
why I
this
did
track,
class.
been around this track before.
I'm still a baby, hold on.
That's so funny.
Okay, good.
So why, I wonder why, usually you can go to the relativistic limit and it works, right? Is there some approximation in this equation?
Oh, yes, of course.
I forget.
The approximation is that in the relativistic form, G is mc squared gamma. And P is equal to mc beta gamma. And so mc squared gamma is mc squared times 1 over the square root of 1 minus beta squared, which is b squared over c squared. And so we can write this as approximately equal to mc squared plus 1/2 v squared over c squared. Whoops, 1/2 v squared over c squared times c squared, which is mv squared, plus other higher order terms. So this is the classic moment, the classic Newtonian momentum, and this is the rest mass. And then there are the higher order terms. But it's this ratio, E over mc squared, that is what people call the relativistic gamma. And when this number gets to be large, then it's in the relativistic domain. In other words, when the velocity is some fair fraction of the speed of light.
What is the, I mean, so like if we calculated out the energy and we got 2 GeV over C instead of 2 MeV over C, then we're going to have to go into relativity.
Yeah. It'll be somewhere in between. So let me tell you a practical example of this that we're working on in the lab over here. So we're making this little detector of a mini time cube, which is for detecting newibars. And what we're looking for is the reaction nuibar plus proton goes to an E plus a neutron. So in comes the neutrino unseen, whacks a proton, and this is newibard, produces the positron. And it could be the other way around, but this is the interaction that is more prominent for the low energy. And these are the kind of neutrinos that are emitted from reactors and things like that. The sun emits mostly neutrinos, reactors, antineutrinos. And so out comes the positron and out comes the neutron. Now the amusing situation for exactly the energies under discussion here is that this energy is a couple of MeV. So this guy gets some fraction of the energies, a fair fraction of the kinetic energy, and this guy gets most of the momentum. So it's very confusing. So in practice, what happens is most of the time, if you draw a picture of the velocity vectors, the neutron is going pretty much ahead, and the positron comes off at some angle. So I always tell people that in this weird little circumstance, you can think of it as the positron gets the kinetic energy and the neutron gets the momentum. But it is amusing to think about it because it's in this mixed domain, and one is relativistic and one isn't. So in fact, we measure the positron energy to get the energy of the neutrino, but if we want to get the direction of the neutrino, we need to measure the neutron direction, which turns out to be not easy. So that's the game. Anyway, okay, onwards. And we have to clear out of here. Oh, what do you guys think about moving over to the conference room for the class? And then we won't get harassed by Eric and we won't have to wait for John to get out of here. Then the conference room is clear.
If it's fine with them, it's
3, 6,
fine by
8 of
me.
us
Yeah, we're fine with that.
should be okay.
I'm good.
Okay, so let's start on Wednesday by trying to meet in there. I think it's free and Karen can book it for us. And then we won't have Eric lurking. He sent me a nasty gram this morning saying, I would appreciate it if you'd be out of there.
No way.
Nasty saying I would appreciate it.
Well,
That's
you know.
nasty.
Not as nasty as Eric is.
Okay, but, yeah, and John always runs over just like I always run over. Say like Aaron.
It's the war.
So, okay, that was why I put that problem in, wanted you to see that situation. Then there was number 18. Okay. Do we want to go through 18? Did people have trouble with that? I mean, you can see right away what those equations are, right?
Hooke's law, right?
So you see, yeah, what are those the equations of? They look suspiciously like the equation of an ellipse, right?
Yeah.
So you say to yourself, oh, I know what's going on here.
Actually, it's circle, right? If k's were the same.
Well, yeah, if I set it to be the same, it's a circle. Or, you know, I could set it up to be slightly asymmetric, so it would be an ellipse.
Yeah, we talked about that one. We talked about 20, right?
20,
How we didn't really,
well, okay, did any of you meet the challenge?
I got full points on the problem, but I didn't tell them.
Does anybody know what type of system you could get that equation of motion from? I still don't.
no beer for me.
There's something with
Yes.
units of energy.
I don't have like a great idea, but it seems like if you're looking at, just very vague, if you're looking at something with like a total energy that's somehow like positive and, or something where your kinetic energy and your potential energy are adding to a positive quantity and then all of a sudden adding to a negative quantity, they go through zero somewhere, and at that point, it seems like you might not have to have your acceleration be the whatever, the partial v, partial x, or.
Wait, you're saying energy is positive and then passes through some point and it becomes negative?
Yeah, if you have, yeah, like if, I don't know, if you assign like some signs to, like, say your potential is negative, if you eventually, if the sum of these two things, it was like positive for a while, and then you go to like a region where it's negative, like maybe like a bound state becoming unbound, at the exact moment when it's becoming unbound, your like classical motion equations aren't necessarily true based on whatever this Lagrangian is that they cooked up. I don't really know.
Well, F times T in this problem is 0. Wait a minute.
F times what?
F times T is 0 in this system.
T being the kinetic energy?
Yeah, sorry, T being kinetic energy. So force times kinetic energy is 0 in this problem. That doesn't mean it has to be at rest.
What about
We're talking about a not moving particle?
the Lagrangian here effectively has units of like energy
Or constant.
squared, right?
Yeah,
Right.
which is pretty.
Yeah, one thing that, or you do something like that is like when you look at like the Einstein-Hilbert action. Because, you know, you look at the geodesics on the metric, and that's in terms of energy squared. It has units of energy squared.
That's right, and indeed, you can set up, oh no, I started to say something wrong. You can set up the Lagrangian in terms of accelerations as well, but that's not this line.
Mhm. Yeah, just going with the you know, just
The units.
Yeah,
energy
dimensions.
squared. Mhm.
Oh. That's interesting. I'll have to think about that.
Did anybody check the solution to see if they have a?
I did, and I actually went on the web to see if I could see something else. And my first thought was seeing the x dot squared in there was going to be some lost term, but then I couldn't make that work. So I don't know, maybe someone just cooked that up out of, it's an odd looking equation and it's legal, even if it's not sensible.
I think maybe they wrote it wrong.
Could be, I don't know.
I mean, it factorizes like the equation of motion, yeah?
Yeah.
Yeah, I just kind of, I just said I don't know what it is. I don't know what the motion is, but I mean, there's things in there that that kind of makes you feel good about it, like F equals ma and total energy.
Maybe that was the whole point of the problem, to make you worry a bit. Okay, so then 23 was the next one, particle falling gravity with the old p squared dissipation law. What happens when you jump out of a building? Or you jump out of an airplane and your parachute doesn't open?
And you got yourself a terminal velocity and whatnot.
Right, so that's not a hard problem. You've all done that, I think, probably twice as an undergraduate already, right?
Maybe not with this method, but
But not this method. But I presume everybody, oh, the other thing Keita complained to me about was, he said, an awful lot of people in this chapter, this last section, that their problems were looking like, their solutions were looking like the Goodman set of solutions that are on the web.
maybe his solutions are just look like ours.
Okay, just.
Maybe there's just one way
Most
to
of these
solve
are
them.
like
Yeah, that's
pretty
not what I'm
standard,
wondering.
like
I don't know
how are you
what
gonna
some
solve
Some
this
of them
differently,
you
you know?
can't do much differently, but you go to following the same order and notation.
Yeah.
But look, if you.
How do you find those
examples?
How do you find those solutions, by the way?
Google.
We were trying to Google this.
Yeah, we tried to.
Number 6 yesterday to no avail.
Because we
It's
spent like
we
6
spent
hours
too
straight
long.
on it, and we're like, well, let's see if
Oh, really?
how they start the problem.
Yeah.
We couldn't find
Actually,
the
so
solution.
I went onto Wikipedia and found the hypocycloid, and then because at some point I just gave up integrating it and are trying to figure out the solution to it. So I just like, you know what? If they're saying that they show that this thing's a hypocycloid, then the x must have the form cos theta sine theta, something like that.
Yeah.
And so I mean that's kind of where I got help with that one for number 6. You guys were looking last night.
Yeah, you just look if you jump to
Okay, but
hypocycloids.
I don't mind that if you've tried and struggled and then need a little hand at it, that's.
Yeah, especially
that's
like,
okay.
it was just over the weekend.
That's okay. What I want for you is for you to struggle with the problems and think about them. And
Good work with the hypocycloid one. Job well done.
Yeah, mission
Okay.
accomplished.
so,
This one though.
I want to try to knock off then this chapter 2 this week so we can, as I told you, so we can push ahead. I don't fix the web page yet, but everybody has the problem assignments for this week, right?
So I think that the thing about chapter 2, and just so you can kind of keep this in the back of your head when you're showing us, is I was having trouble, I guess in chapter 1 they did nice generalized coordinates for me with the q dots and the q's and all that kind of
Yeah.
stuff. even though I didn't find that nice at first. With the chapter 2, when they were doing the examples, they did a lot of like y dots, and then all of a sudden y dot wasn't the DDT, it was the DDX instead. And so, I mean, if maybe you can, like, when you're going over chapter 2 with us, if you can kind of point out how to be careful with that kind of stuff. Because I was doing my homework with John, and he was basically burning me a lot on like, well, here's how you switch your variables. And
Yeah,
so, I mean, once I was able to do that, I think that this wasn't that bad, but I was getting fooled a lot on the X dots and Y dots when they were just switching the variables.
okay. Specifically, where are you seeing that?
Go look at the examples there.
Yeah, I was,
They just change notation, so they don't use it for DDT, they just use it for D, whatever variable they're differentiating with respect to. I mean, integrating with respect to.
yeah, and just switching that up, like, was a little bit disorienting for me. I'm also just showing off my stupidity.
No. The chance, as I've said before, the chances are if you have a question, others have the same question.
Yeah, so like in 211 on page 38, he was just doing f of dy.
Way back on 38.
Yeah, that's where I'm at.
Oh, okay.
He was just going straight dxd, y dot and whatnot. But when we changed to like, I mean, even like the first problem, the free particle in space proved that it's a straight line.
Right.
I was, at first I started off, I was going like, okay, well, ds equals dx squared plus dy squared plus dz squared. Let's do the dot as a function of, ddt, but, I started working through that because I didn't know which one.
Okay.
Well, why do I choose x as my function I'm taking the derivative with respect to?
That's the independent variable in your functional.
Yeah, I think that's what I kind of figured out in the end.
Yeah.
So you see a big crossed out section of my problem number 1.
Uh-huh. So in fact, in playing this game, you can set the description of the variation about the line, for instance, doing the straight line problem. The way I always like to think about it is, if I want to do the 2 points, show that the shortest distance is a straight line, then I can draw any old function as the perturbation about that. And then I'm going to do the Fourier transform of that function. But I could, in fact, use any old expansion, complete blah, blah, blah function. I use the sine transform, in fact, which is zeros at the end. Then I know that that's going to work. So I'll have all of these components, which are the product of the sine of that particular period that I'm trying, which is going to have to work out to be an integer multiple of the distances, times the function. That'll give me the coefficients. And so because of it being the sine function, you're going to therefore get 0 for all of these components. And you're done. You just did all functions. Because you can show that each of the components will have to be 0. But you could have used Legendre polynomials or whatever tickles your fancy.
Power series.
Huh?
Power series.
Yeah, power series, which is one that is alluded to. Now I get confused because I've been looking at this book and at Landau. He did the power series case in here, I think. Oh, I forgot.
Who, Goetze?
Yeah,
I don't remember seeing
I
power
don't remember
series.
that.
no.
Well, we have like a
anyway.
problem where we have just well, it's not a series, it's just a polynomial.
Which
Yeah,
one
yeah,
is
okay, it was one of the problems.
Yeah.
Oh, yeah, problem 5, as a matter of fact.
Yeah.
A plus BT plus CT squared.
Well, yeah, our problem, but
Yeah.
he didn't do it.
No, you didn't do it. But you could have gone on and put in a lot more terms.
Mhm.
But I'm down on power series expansions. Mike, well, we're gonna have to finish up, but let me give you my power series rant. My students often are using CAN programs. And so an easy thing to do, for instance, to fit the response of a photomultiplier, the output signal versus the input light. So you would like it that the output charge is proportional to the number of photons that hit the phototube, but they're not. They saturate. And so you have to fit some function to the response of the phototube. We do that when we're calibrating light detectors. So you have some response that plateaus out like this as a function of the amount of illumination and the charge that you get out. And so if you're lazy and you're using Root or one of those things, then you get some data points like this and you go, oh, okay, I'll just do a power series fit to this. And it turns out it takes a lot of terms to get a reasonable fit to it. But if you look at it and think about it for a little while, you say, oh, this actually works much better if I do 1 over Q, and so the fit is a 1 over Q0 plus a 1 over some other constants, and it fits without using many terms. But if you just blindly go and do a power law fit to this, it'll give you a whole string of terms, and power laws are unstable as hell if you go outside the fitting regime. And I hope all of you, this is the kind of things that theorists don't tell you. But experimentalists learn it by sad experience. You fit it over some region, and we had this happen in one of my experiments that were we had data over some regime like this and did a power law fit to it, but the fit was unstable, so that if you went outside the regime where it was fitted, it just went crazy. So people, well, actually in this case, it went like this. And people were up in this regime exploring, saying, whoa, look at that. What a marvelous behavior. This is not physical at all. And this is because a power law was used to fit something that is actually an exponential, or more near to an exponential. So let that be a lesson to you. Look at the physics of what you're trying to fit up, and try to write a function that's physically sensible to start with, and you won't get yourself in so much trouble. Right. The little things our theoretical friends won't tell us. Okay, so we better quit. I don't want Eric on my case. Let's go.